Bismillahirrahmanirrahim. Assalamu alaikum dear students. This is your instructor Anisa Nawaz from Department of Physics. This is our lecture number 12 from chapter number 2, Vectors and Equilibrium. This is our third lecture related to chapter number 2. In the previous lecture we have discussed about addition of vectors, properties related to addition of vectors, multiplication of a vector by a scalar, and subtraction of vectors. After today's lecture, you would be able to explain resolution of vectors, components of a vector. You would be able to calculate magnitude of vector by rectangular components, and you would be able to determine angle of vectors. Okay, let's consider example of an aeroplane moving, and this is basically vector representation of velocity. Okay, you can see that here in first case, direction of velocity of aeroplane and direction of wind both are along the same direction. So as we have discussed earlier that both these vectors will be added and velocity of the aeroplane will increase. In second case, direction of velocity of aeroplane is in this direction and headwind is there. The wind is blowing in the opposite direction. So these two vectors will be subtracted. But in this case, when aeroplane is moving in the forward direction and there is crosswind, wind is blowing in this direction, then what would be the direction of motion of aeroplane? How we are going to check that out? You will see that how aeroplane will move. You can see in first case as vectors are added. So what is happening? Velocity of aeroplane is increased. In second case, as wind is blowing opposite to the velocity of aeroplane, so speed of the aeroplane is less because vectors are subtracted. And in third case, when crosswind is there, aeroplane is moving diagonally. It is making some angle. So how this angle can be calculated? For that we need resolution of vector, we need components of the vector. Similarly, if we are considering another example, again that if we are standing over here and now we know that what is the exact location of library, we have to go to library, and we know the exact distance and exact direction of the library. Still, it is not possible for us to go directly towards the library. Okay, we cannot follow this straight path, we cannot follow this position vector, but we have to follow such a path in which we have to divide the vector, position vector, into its components. So for that we need the process of resolution of the vectors. Okay, so we need resolution of the vectors for various purposes. That is very important because sometimes we cannot use vectors directly. So what is basically resolution of vectors? We can define resolution of vectors as the process of splitting a vector into two or more vectors is called resolution of vector. We have to resolve the vector basically. We have to split the vector into its components, into the vectors. Okay, and the vectors so obtained are called components of a vector. We are dividing a vector into its parts. Okay, we are dividing the vector into two or more vectors such that when we will add those vectors, we will get the same answer. Okay, so what is component of a vector? How we are going to define component of a vector? The effective value of a vector in a particular direction is called component of a vector. Effective value of a vector in a particular direction means that if we are applying force at some angle, then what is the effective value of force in horizontal direction, what is effective value of force in vertical direction? Those effective values are basically components of that force. So we can say that the effective value of a vector in a particular direction is called component of the vector. And process of resolution is opposite to addition. Sometimes we think that opposite to addition is subtraction. No, opposite to addition is the process of resolution. In addition, we are adding two or more vectors to get one resultant vector, and in resolution we are resolving one vector into its components into two or more number of vectors. So basically process of resolution is opposite to the addition. Okay, so if you are talking about different vectors, let's say we are having all these vectors and we want to check out that how many components of a vector are there. We are not applying any condition, we are just talking about the components of this particular vector. So you can say that we can draw components like this, because if we are going to add these two vectors, we will get this resultant. We can have these components, 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 these and these components. So we can have the components, we can divide a vector into so many components. So if you're asked that how many components of a vector are possible, then we are having infinite number of components. Okay, we can resolve a vector into infinite number of components, but over here we don't require all these components. Okay, we don't require all these components, we just need particular types of components which are known as rectangular components of a vector. We just need rectangular components of a vector. What are rectangular component of a vector? If the components in which a vector is split are perpendicular to each other, such components are called rectangular components of a vector. These components are very important because with the help of these rectangular components, we can add these rectangular components and we can find a resultant vector. This process is simple because if you are having a right angle triangle, we can apply Pythagoras theorem and we can find out the resultant vector. So important word is rectangular components of a vector, those components which are at 90 degrees to each other. These components are known as rectangular components of a vector. So how we are going to say that why components are important? Adding vectors graphically provides limited accuracy. We have already done this, we have added vectors graphically and we have to use the scale, but it is not providing us a very accurate result. Vector components provide a general method for adding vectors. You will see that if we are having components of a vector, then we can mathematically add those components to get exact resultant. It will give us more accuracy because graphical method is not providing us very accurate result. Any vector can be represented by an x component ax and a y component ay. So if you are having any vector, we can resolve into its components x component and y component. Okay, so let's check it out how we are going to resolve a vector. Let's take coordinates x prime and y prime. Okay, we are having x and y coordinates. We are having, let's say we are having a vector starting from the origin. Tail of the vector is at the origin and head of the vector is over here. So this vector is considered and this vector is denoted as vector A, and don't forget to put arrowhead. This OP, which is basically vector A. Now what we have to do? We have to resolve this vector into its components, horizontal component and vertical component. For that purpose, what we have to do? We have to draw the projection of this vector along x-axis and along y-axis. Projection means shadow, exactly downward shadow. If we are having this vector and we are drawing its shadow on this x-axis, we are drawing its shadow on this x-axis, this will be its horizontal components, and if we are drawing its shadow along this y-axis, then it is its vertical component. How we are going to do that? You can see we are dropping its shadow along the y-axis basically. Okay, so this AY, you can see that it is equivalent to this along y-axis. So this is vertical component. Okay, vertical component of vector A, which is denoted by vector AY. Then we are dropping its projection along x-axis, which is denoted by AX vector. You can see that it is equivalent to this AX vector. So right now we are having two rectangular components of vector A. Okay, we are having two rectangular components because right now we are considering a plane vector which is basically lying in a plane, two-dimensional. So we are having two rectangular components. If we are having space vector, three-dimensional vector, then it may have three rectangular components along z-axis as well. But right now we are considering a plane vector, so we are having a horizontal component and we are having a vertical component. So this is the process of splitting a vector into its components, rectangular components, which is known as resolution of a vector. And this process is very important because in the next article, when we will add vectors by using its rectangular components, then we have to use this concept. So this is vector represented in terms of its rectangular components. Okay, so vectors can be represented in terms of its rectangular components as A is equal to AX plus AY. Means while we are going to add these two vectors, then what will happen? We will get the same result. This is the condition, that if we are resolving the vector into its component, then when we will add those components, we will get same original vector. So we can say that vector A is equal to AX plus AY vector. And we know that vector can be completely specified by its magnitude as well as direction. And we know that along x-axis we can have a unit vector I hat, okay, and along y-axis we are having a unit vector j hat. So if we are using the magnitude of vector with its direction ax into I hat, and magnitude of vector along y-axis ay and its direction j hat. So we can say that this vector can be represented as vector A is equal to ax I hat plus ay j hat. Okay, so this vector can be written as, okay, if we are talking about three-dimensional space, we know that the unit vector I points in the positive x direction or negative, okay, because that will be minus I. J points in the y direction and k hat points in the z direction. Any vector can be expressed in terms of its components as, now if we are having a space vector, if we are having three-dimensional space, then same vector A can be represented as AXI, x component along x-axis, AY j hat, vertical component along y-axis, plus AZ k hat, z component along z-axis. Okay, so a vector can be divided into its rectangular components as ax, ay, az along their particular directions. Okay, because we know that I hat is representing along x-axis, j hat along y-axis, and k hat along z-axis. So we can resolve a vector into its rectangular components along its constituent directions. Okay, so if we are going to represent the vector in terms of its components, then what we have to? We have to consider triangle OPQ as a right angle triangle. We have considered a vector vector A as OP. Now we are converting that vector without any direction. We are just considering it as a rectangle, right angle, not rectangle. We are considering it as a right angled triangle because we are going to use trigonometry to solve it. So we are using it as a right angled triangle. Okay, so we are having this theta A, and we are having, you can see that we are having this as angle of 90 degrees. So this is right angled triangle. So that was basically one of the reasons that why we were only considering rectangular components, because we needed a right angle triangle so that we can apply Pythagoras theorem and we can solve this equation for the components. Okay, and we are having vertical component and horizontal component. So for horizontal component Ax, what we have to do, don't forget to put arrowheads over here. Okay, so for horizontal component Ax, we know that cos theta is equal to base over hypotenuse. We are using trigonometry over here. Base over hypotenuse. Cos theta is base over hypotenuse, and in this triangle, this adjacent side is basically the base. OQ is base, so we are putting OQ in place of base, and opposite side QP is basically perpendicular, base over hypotenuse. So this side OP is basically the hypotenuse. So we can put OQ in terms of base and OP in place of hypotenuse. So cos theta is equal to base over hypotenuse will give us OQ over OP. And magnitude, we are just talking about magnitude over here, so we can write it as Ax divided by A. Ax base, A hypotenuse. You can see here Ax is base and A is hypotenuse. So what we will do, we will multiply this A over there, we will separate out Ax, and we will get Ax is equal to A cos theta. This is basically horizontal component of vector A. Ax is equal to A cos theta. Okay, name it as equation number 1. So this horizontal component, if we know the magnitude of the vector and if we know the theta angle which it is making with the horizontal, then we can find out its horizontal component. And if we are talking about vertical component, for vertical component we will consider sin theta. Sin theta is equal to perpendicular over hypotenuse. Okay, so perpendicular is PQ, and hypotenuse is OP. So we are going to write it as PQ divided by OP, and PQ is AY and OP is A. So we can write it as AY divided by A. So if we are going to separate out AY, then we can write it as AY is equal to A sin theta. So this is basically the vertical component of vector AY, magnitude of vertical component, that is AY is equal to A sin theta. Name it as equation number 2. So we have now calculated horizontal component and vertical component of the vector. Ax is equal to A cos theta and Ay is equal to A sin theta. So now this figure which we have drawn over here, vector A resolved into its horizontal and vertical components, Ax and Ay, it can now be drawn as this. Okay, it can be now drawn as Ay is equal to A sin theta and Ax is equal to A cos theta. Okay, so we can say that these components of A are Ay is equal to A sin theta and Ax is equal to A cos theta. So we know that as A is equal to Axi plus Ayg, so we can put the values of Ax and Ay over here. Vector A will now become A cos theta I hat plus A sin theta j hat. So vector A in terms of its component can either be written as Ax I hat plus Ay j hat or A cos theta I hat plus A sin theta j hat. Okay, so these two representations are for the vector representation of vector in terms of its rectangular components. So let's check out an example. That let's assume that vector F is 30 newtons of force. It is acting at an angle of 20 degrees to the x-axis. Based on this information, we can find out horizontal and vertical component. We are just provided with the magnitude and angle of that particular force. So horizontal force, x component of force, we can put the formula Fx is equal to F cos theta, and we know that magnitude of F is 30 Newton given and theta is 20 degrees. We can put these two values and we can get the resultant. Fx is equal to 30 Newton into 0.940, which is equal to 28.2 Newton. So we were provided with the magnitude and direction of the given vector, and we have calculated its horizontal component. Similarly, we can find out its vertical component. Fy is equal to f sine theta, again putting the value of force, and we are now having this value 10.3 Newton. So 28.2 Newton is the magnitude of horizontal component and 10.3 Newton is the magnitude of vertical component. Okay, so this force of 30 Newton is basically having these two components. Okay, so if we are going to calculate magnitude of the vector from its rectangular components, then how we are going to do that? If we know the rectangular components of a vector, then we can find out its magnitude without using the scale. We don't have to use the scale for from right angle triangle. Again, we are considering same triangle OPQ. By Pythagoras theorem, we can say that we know that Pythagoras theorem is hypotenuse square is equal to base square plus perpendicular square. Okay, so taking square root on both sides, we can say that hypotenuse square under root is equal to base square plus perpendicular square whole under root. Okay, so this under root means power of 1 by 2. You know that under root means power of 1 by 2. So that 1 by 2 will be cancelled with this 2, but these cannot be cancelled because we are having a plus sign, and this under root cannot be applied separately on these two values. So this under root will only be cancelled on left hand side and it will not be cancelled on right hand side. So we can write it as hypotenuse square is cancelled is equal to under root base square plus perpendicular square. So we can say that hypotenuse is equal to under root base square plus perpendicular square. And in this triangle which we have considered, OPQ triangle, we have considered this thing that hypotenuse basically is OP, okay, which is vector A, and we are talking about the magnitude, we are not considering the direction. So we can write it magnitude of A in place of hypotenuse, and under root AX square, base is basically AX and perpendicular is AY. So we can write here that AX square plus AY square with under root. Okay, so magnitude of A is under root AX square plus AY square, and in 3-dimensional space vector A can be written as under root AX square plus AY square plus AC square, and don't forget to put the arrowheads. Okay, so if we are having 2 dimensions, then AX square plus AY square, and if we are having 3 dimensions, then AX square plus AY square plus AZ square. So in this way, if we are having the components, horizontal components and vertical components of a vector, we can find out the magnitude of that vector. Okay, we can find out magnitude of that particular vector if horizontal and vertical components are provided. So you have to learn this formula: magnitude of A is equal to under root AX square plus AY square, or magnitude of A is equal to AX square plus AY square plus AZ square, depending upon the dimensions. Now if we have to find out direction in right angle triangle, or we can say that direction of a vector which is provided, how we are going to find out that direction, how we are going to find out theta with the help of rectangular components. To determine the direction in right angle triangle OPQ, we know that for direction we use tan theta. Tan theta formula for that is perpendicular over base, and in the given figure we are having perpendicular as AY and base as AX. So we can write it as AY divided by AX. Tan theta is equal to AY divided by AX. Okay, we can write it as theta because we don't need tan theta, we need direction only, we need theta only. So we will separate out this theta by applying tan inverse on both sides. That tan will be cancelled with tan inverse, and on right hand side tan inverse will be left. Tan inverse of AY by AX. So if vertical and horizontal components are provided, then we can find out the direction of resultant angle as well. Initially we have calculated magnitude of resultant vector with the help of components, and now we are calculating direction of the resultant vector with the help of rectangular components. So theta is equal to tan inverse of ay by ax. Equation number 7, you also have to learn this equation. These equations for magnitude and direction are important. Okay, magnitude is equal to under root fx square plus fy square or ax square plus ay square. It's up to you that what are you giving the name to the vector. Okay, and theta is equal to tan inverse of ay by ax. Okay, let's consider an example that we are having a lawn mower and in which we are applying some force. That force is applied in this direction, but lawn mower is moving in the forward direction, so we cannot apply force directly over here. We cannot calculate force directly over here. All the force is not responsible for the motion of lawn mower, so we have to resolve this lawn mower into its x component and vertical y component. Okay, so force applied to the lawn mower may be resolved into two components, x for the horizontal and y for the vertical components. Then we can calculate that how much force will be applied if we are placing the lawn mower at which angle. Okay, so we can calculate the resultant force. Let's consider another example, that if you are having a ball, why does a ball move faster on a steeper slope? If you are having a steeper slope, then ball moves faster. Okay, what is the reason behind that? We can check that out. We can see what happens when we resolve the vector representing weight into its components. What happens, you can see here, we are having a ball which is in different positions. You see that no slope at all and ball is at rest. Okay, we are having little steeper slope and you can see that ball is moving with some acceleration. More slope, more acceleration, and maximum slope means maximum acceleration. Okay, so in this figure, if we are having vector A represents the amount of acceleration of the ball and vector B presses it against the surface. So we can say that steeper the slope, more acceleration will be there. You can see that we are basically resolving a weight into its constituent component. So over here weight is acting downward, no acceleration. Weight over here, but this weight is now resolved into horizontal and vertical component, and this component of weight is basically responsible for its acceleration, for its motion. So you can see that length of this vector is increasing if slope is increasing, so it means that more acceleration is produced. This component of weight is increasing, that's why acceleration is increasing. So in this way, components of weight are important to determine that why a ball is moving faster on a steeper slope. So we can use trigonometry to find the components of a vector. Ax is equal to a cos theta and ay is equal to a sin theta, where theta is measured from positive x-axis towards the positive y-axis. Okay, you have to keep this in mind that while we are talking about theta, this theta is with positive x-axis and it is always in anti-clockwise direction. Theta is always measured in anti-clockwise direction. Okay, we cannot measure theta in the clockwise direction. That will not be theta, that will be given some other name, but that will not be theta which we are using in these formula. Okay, this theta is basically the angle measured from positive x-axis and it is in anti-clockwise direction. So we have seen this thing that if we are having a plane vector, then we are having two rectangular components, and if we are having space vector, then we are having three rectangular components. So a vector can have infinite number of components, but it can have a maximum of three rectangular components. Rectangular components, those components which are perpendicular to each other, which are having angle of 90 degrees between them. Okay, so if we are talking about another example, an 80 km/h plane flying in a 60 km/h crosswind. Okay, what is the plane speed relative to the ground? If we are having an airplane which is moving in this direction with the speed of 80 km per hour, and a crosswind is there which is 60 km per hour. It is acting in this direction, and we are considering the scale 1 centimeter is equal to 20 km per hour. According to that we are drawing it. Okay, so that will be 4 centimeter and this will be 3 centimeter. So how we are going to calculate the velocity, resultant velocity of this plane? For that we have to calculate magnitude. We know that we have to draw vector representation of the velocities involved. Okay, you can see over here we have to use head to tail rule. We will use this vector first and then we will move the second vector over here, head of the first vector to the tail of second, in this way. Okay, we have to connect these two vectors and then we will find out the resultant by joining tail of first to the head of last. In this way we will find out the resultant, but we are not going to calculate it, measure it with the help of a scale. We will use trigonometry to solve it. Okay, use Pythagoras theorem to find resultant. How? We know that we are having hypotenuse square is equal to perpendicular square plus base square. So we can write it as r square is equal to 80 square plus 60 square. We will solve these. We will take under root and we will find out the result as 100 kilometers per hour. So the velocity will be 100 kilometers per hour. The magnitude of the resultant velocity is 100 kilometer per hour. That this result is more accurate as compared to the result which we will calculate with the help of scale or graphical method. Okay, so if we are going to find out the direction of vector, direction of velocity, then what we will do, as velocity is a vector, we need to find the direction of the vector. We can do this by finding an angle alpha within the vector diagram. We can name it as alpha over here. Most of the times we name it as theta, but right now we are saying it as alpha. How? Again, by using the formula, using trigonometry, we can say theta is equal to tan inverse of perpendicular over base. Perpendicular is 60 and base is 80. Okay, perpendicular 60 and base is 80, because you know that the side which is having both 90 degrees angle and unknown angle, that is always base, and the side opposite to the unknown angle, that is the perpendicular. So the 60 is perpendicular and this 80 is base. So we can say over here that theta is 36.9 degrees, the exact value. Okay, 36.9 degrees is the angle. We have calculated magnitude as well as direction with the help of trigonometry. Okay, so the answer should include both the size and direction of the velocity vector which we have calculated. So we can say that the velocity of the plane relative to the ground is 100 km per hour at 36.9 degrees to the right of the plane initial velocity. Okay, from figure we can say that it is to the right of the plane's initial velocity. In this way we can calculate magnitude of the resultant and direction of the resultant. And keep this in mind that the components of a vector can be positive or negative numbers. Okay, we can see component of a vector can be positive or negative. For example, if you are having angle in this vector in this direction by making this much angle, okay, and we are resolving it into horizontal and vertical component, so its horizontal component will be in negative direction and vertical component in positive direction. Okay, or if you are having angle in this direction, then its horizontal as well as vertical components both will be negative. Okay, but keep this in mind that whether the components of a vector are positive or negative, it doesn't matter. You can see over here that if the vector lies in the first quadrant, both the components are positive. If vector lies in the second quadrant, then x component is negative and y is positive. If it lies in the third quadrant, then both x and y components are negative, and if it lies in the fourth quadrant, then x component is positive and y component is negative. Okay, so component of a vector may be positive or negative, but the magnitude of the resultant vector is always positive. Okay, components of a vector can be negative, but magnitude of vector is always positive. What is the reason? Because you have calculated the formula. Magnitude of A is ax square plus ay square plus az square. Okay, and if we are putting the value of the component, even if it is negative, due to square it will become positive. Okay, so that was all for today's lecture. I would like to end my lecture with this quote, that I am just a child who has never grown up. I still keep asking these how and why questions. Occasionally I find an answer. Stephen Hawking. Okay, so never ever hesitate to ask the questions. This is a good thing. Question, while you are doing more and more questions, you learn more. So make a habit of asking questions. Okay, thank you so much, girls.